In this video, we're going to look at how acceleration and velocity relate to one another. And typically we depict this relationship through a motion diagram. And there's an example of a motion diagram right here of a car. Basically view it as a snapshot at various points. So at each of these points, this was just a snapshot taken of the car. And the diagram gives you the position and it gives you these velocity vectors. And so if we notice in this one, all of these velocity vectors are the same size. So that means the velocity is constant. It's uniform. It is not changing. It's the same direction, same magnitude throughout this picture here. So what that tells us about acceleration is that the acceleration is 0 because there's no change in velocity. In this diagram, however, we have a little different situation. We see that the cars are more closely together at this end and they are farther apart over at the right end. And we also notice that the velocity vectors are increasing. And so if the velocity is increasing, well, that means there has to be an acceleration, and the acceleration is in the same direction of that change. Since we go from small to big, our change goes in that direction. And so our acceleration is in the direction of the change. We're increasing our accelerations to the right. Now, looking at this diagram a little further, we see that the acceleration is the same throughout, so we see that this is uniform acceleration, but the velocity is increasing. It's just the rate at which it increases is the same throughout the entire situation. And since these are going to the right, we say that it is positive velocity and positive acceleration. In this third diagram, we see we have an initial velocity, and we're still moving to the right, so we have a positive velocity. However, the cars are starting to get closer together as we take our snapshots, and so this car is slowing down. All right, the vectors of the velocity are getting smaller as time goes on, and so the change is going from big to small, so that tells us that our change is to the left, or it's a negative change, which corresponds to our negative acceleration. Once again, this is a uniform acceleration. The rate at which velocity is changing is not changing. It's constant, but it's in opposite directions. So to summarize these three situations, when we have a velocity that has 0 acceleration, we see that the velocity does not change. The car neither speeds up nor slows down. It just remains at the same speed in the same direction. The velocity is constant. However, when the velocity and acceleration are in the same direction, now this is constant acceleration, but velocity and acceleration are the same direction, we see that we speed up. So if both are positive, we speed up. Or even if both are negative, because they're in the same direction, we would also speed up. We would just be speeding up in the negative direction. And the third situation, where they are in opposite directions, we have a positive velocity and a negative acceleration. We see that the car is slowing down. When acceleration is constant or uniform, we have 4 equations that come about and can be used. And we're going to discuss each of these equations and their benefits in a moment. But understand that these 4 equations are only viable when acceleration is uniform or is constant. So write these on a formula card that we can use on tests and quizzes. However, we've got to understand that it is only useful when acceleration is constant. Each of these equations has their own personal effectiveness, so to speak, in that they have a benefit to each. And so this first one, saying that the displacement is equal to the average velocity times time, well, this just gives you the displacement as a function of the velocity and time. So if we have velocity and time need displacement, well, this is a good one to use. And we don't want to use this, however, when we're asked anything about the acceleration, or if we're given the acceleration and need to use it. So if our situation doesn't deal with the acceleration other than we know it's uniform, then this is a great equation to use. However, if you're in a situation where you don't know or aren't asked anything about the displacement, well, then we want to go to this equation where we have the final velocity is equal to the initial velocity plus the acceleration times time. Now remember, this comes from the idea that acceleration is equal to the change in velocity over the change in time. And really, change in velocity is simply v minus v naught, or the final minus initial, over time. Use some algebra and you get back up to this equation. And so when we don't have displacement, we can use this. This gives us our final velocity in terms of some initial velocity and the uniform acceleration and the time that it takes. We can confirm this equation graphically by looking at a linear function on a velocity versus time graph. And remember, the slope of a velocity versus time graph is acceleration, because acceleration is equal to the change in velocity over the change in time. And so if we look at some initial velocity and we want to know this final velocity here, well, that difference is going to be this height, all right? Or the entire velocity is going to be this height. The difference is this height here. Well, what is that height? Well, that is the acceleration, that slope, times this time interval, which is this piece right here. And so this shows that you take the initial velocity plus a times t, and we get the final velocity. This equation is also helpful like before in that if we're looking for displacement, we have our function solved for displacement, but this gives us a little more information, as in, what if we have acceleration and we need to use the acceleration? We don't have final velocity. We only have an initial velocity and a time. Well, if we have that, then we can find the displacement based on this equation. And another way to look at this graphically is to see that the area under the graph of a velocity versus time for any object, that is equal to the displacement, or the change in position. And the final equation gives us velocity, the final velocity, as a function of acceleration and displacement. A lot of times our initial velocity is going to be 0, or maybe our final velocity is going to be 0, and so we can cancel one of those out. And as long as we have acceleration and displacement in the given situation, we can then find the missing velocity. The great part about this equation, it is independent of time. We don't need to know the time that it takes. So if we don't know time, this is a great equation to go to. So we're going to use these equations to do some problem solving. And there's a few hints and strategies that we need to keep in mind as we go through these. So first thing is, for sure, we need to read the problem and we need to understand what the problem is asking. Diagrams always help. Draw a diagram and choose a coordinate system, meaning are we dealing with rectangular coordinates, polar coordinates, whatever it may be. Label any initial and final points. Where are we starting? Where are we ending? And then indicate a direction that's positive. Is it up? Is it right? Is it left? Is it down? Where is our positive direction? We need to make sure that that's clear. And then label all quantities to be sure that the units are consistent, and convert if necessary. We need to be in SI units typically. However, if all of the units are in British units or CGS, then maybe we could keep it in that, but just make sure we're consistent throughout with all of our units. And then choose the appropriate equation, as we just finished going over there. What do we have? What do we know? What do we not know? Which equation is best? Typically, I will ask you to solve for the unknowns first. Do not plug any numbers in until the very end. Solve for your unknowns. You may have to use two equations. May only have to use one. This is where the math is going to come into play. And then plug in the numbers at the end. Check your results. See if it makes sense. And always be sure to check units. Let's look at an example of how we can use these equations. So let's say we have a race car that is initially at rest. So a diagram that we could draw for a race car is just a box. And let's say initially, so that's when time is equal to 0, its position, we're going to say, is at 0, because that just makes it easier. And if it's at rest, its velocity, or its initial velocity, v naught, is also equal to 0. Okay, and so if we want units, we'll say that's seconds, meters, and meters per second. And let's say it has a uniform acceleration. So acceleration is constant, and it's 5 meters per second squared. And it does this over a period of time. And we want to know, what is the velocity, what's the final velocity, when it has moved a distance of 100 feet. So what is this distance? This is our change in x. That's our displacement. Well, right off the bat, we should see that, wait a minute, feet, we got to change that. So how many meters is 100 feet? To convert 100 feet, we want to take the 100 feet and multiply by a conversion factor of 0.3048 meters per foot. So that cancels out with the feet, and we get our displacement to be 30.48 meters. So we're looking for a kinematic equation that can relate our final velocity, which is what we're looking for, our displacement, acceleration, and initial velocity. So we need an equation that is independent of time. That equation is the final velocity squared is equal to the initial velocity squared plus 2a delta x. Now our goal here is to find the final velocity. So to solve for the final velocity, we just need one final step to say that the final velocity is equal to the square root of the initial velocity squared plus 2a delta x, or 2 times the acceleration times the displacement. And so now we have our equation solved for the variable that we want, and we can plug in our given information. Well, the initial velocity is 0, so that's just going to be 0. And so we're looking at the square root of 2 times our acceleration, which is 5 meters per second squared, times our displacement, which was the 30.48 meters. And so we can plug that into our calculator, or just see that 2 times 5 is 10. We'll multiply by another 10, and we get the square root of 304.8. And if we look at the units, we get meters squared per second squared, which when we take the square root, that is going to work out to give us meters per second, which is what we want with velocity. And if we plug this into our calculator, we get about 17.5. Now, you might ask, with significant figures, really we should round this all the way up to 20 because we were only given one significant figure with the acceleration. But I'm not worried about that too much, especially right now. 17.5 is good enough. So that is our final velocity. Well, now let's say, using the same situation, we want to know, how long does it take? So what is the time interval, or what's delta t, to reach that distance of 100 feet, or to reach that final velocity of 17.5? And so we're looking at, what equation can we use that now incorporates time but still uses our given information. Now you might think that we have a final velocity, which, yes, if we have to, we can use that, but we'd rather not use it and still rely on our given information to increase the accuracy of our calculation. So the kinematic equation we're looking for is one that has time but is independent of final velocity. And that's the one where we have the displacement is equal to the initial velocity times time plus 1/2 the acceleration times time squared. And so we have all this information, except we want to look for time. And so we want to solve first before we plug in numbers. But let's use a little foresight here to say that, well, you know what? Our initial velocity is 0. So this is simply 0. So we can say that 1/2 at squared is equal to the displacement. And then when we solve for t, we get the square root of 2 delta x all over a. Now keep in mind that a is inside of the square root in the denominator. And so now we can plug in our information that we had from before, which is the displacement, which is 2 times 30.48 meters. And we're going to divide that by an acceleration of 5 meters per second squared. and this comes out to approximately 3.5 seconds. So it takes that car about 3.5 seconds to travel the 100 feet.